Okay, so let us look at one problem here on the solution of a state equation. So the question reads, find x1 and x2 of the system described by the following state equation. So we are given the state equation here, and we are also given the initial conditions. Okay, so how do we solve this? So there are two methods that I'm going to show you, but in separate videos. So in this video, I'm going to show you how you can solve the state equation using a state transition matrix. And then in the other video, I'm going to solve this problem by using a mathematical way of doing it. Okay, so uh, the solution of a state equation, okay, is given by the following. So first of all, let me write the state equation. Okay, so the state equation x dot is equal to matrix A multiplied by the state plus matrix B multiplied by the input. Okay, so now if we take the Laplace transform of this, oh, by the way, x and u are the function of time. Okay, so the Laplace of this will be s, x of s is the first derivative, and then minus x of 0. Okay, and then we have a x of s plus b u of s. U is also a function of time. Now, as you can see, a problem here. The matrix given here is matrix A, isn't it? We do not have matrix B, right? There's no matrix B here. Okay, so meaning the input is equal to 0. So this is under a natural state condition. Okay, this under natural condition, isn't it? So we are going to let u equal to 0 because as you can see there, we don't have an input. Okay, so we have s, x of s minus x of 0. This is equal to a x of s. Okay, and then let's solve for s for x of s. So this s x of s minus a x of s equal to x of 0. Okay, factorize x of s, we have s minus a. Now, this operation is impossible in linear algebra. S is just a number, okay? It's a complex number. And then you're subtracting matrix A. A is an n by n matrix. There's no way you can subtract a number, a matrix from a number. It's not possible, okay? So we have to make this S as a matrix as well. So you multiply by 1, and 1 in the matrix is called the identity matrix, okay? So we have Si minus A equal to x naught. Okay, and then you have to solve for x of s. So we divide both sides by si minus a. Okay, now the division matrix also in linear algebra again is not advisable. So you have to take the inverse of this matrix. So we have si minus a inverse. So we took the inverse of both sides. Okay, so this inverse multiplied by x of 0. And then to transform this time domain, we take the Laplace inverse of that. So the Laplace inverse of x of s is x of t equal to the Laplace inverse of si minus a inverse x of 0. So this here is what we call a state transition matrix. Phi of t is simply equal to the Laplace inverse of si minus a inverse. So when you multiply by the initial conditions, then you'll be able to find what the solution. Okay, all right. So this solution can be written as what? X of t equal to phi of t multiplied by initial conditions, right? X of 0, isn't it? Okay, now let us first find phi of t. Once find phi of t, then multiply by the initial conditions, we'll be able to solve the problem. Okay, all right. So let us first write the problem here. So we have the state equation. This x1 x2 dot equal to, we have a 2 by 2 matrix Okay, so 2 by 2 matrix is 0, 1. Negative 3, negative 2, I think, yes. And then multiply by x1, x2. And we are given the initial conditions, x1 of 0, as well as x2 of 0. This is equal to 1, negative 1. Okay, so first of all, let us okay, I know it's not very necessary, but let's first find the eigenvalues of this matrix. So what are the eigenvalues of the matrix? The eigenvalues matrix is determinant of what? Of this characteristic equation of the open loop transfer function Si minus A. Okay, those are eigenvalues. Okay, so let us substitute. What is Si? Remember, our identity matrix A is a 2 by 2 identity matrix, since our A matrix is 2 by 2, isn't it? So remember that our identity matrix is given by what? 1, 0, 0, 1. Okay, so meaning if you multiply by S, this becomes you multiply the identity matrix by S, you have Si equal to S 0, 0, S, and then you subtract this from matrix A. Sorry, subtract matrix A from this one. Okay, so S 0, 0, S minus matrix A. Matrix A is 0, 1, negative 3, negative 2. Okay, so this is equal to S. So S minus 0, that's S, and then 0 minus 1, that's negative 1. 0 minus negative 3, that is positive 3. And then 0 minus negative 2, that is S plus 2. Oh, sorry, S minus negative 2, that is S plus 2. Okay, and then let us find the determinant of this. Okay, the determinant of this is equal to what? So you just multiply S by that. Okay, so S plus 2 minus 3 by negative 1, right? So this is simply equal to S squared plus 2S plus 3. And then let's find the pose. Okay, so S1, the pose, S2, this will be equal to, using quadratic formula, that's negative 2 plus or minus B squared, which is 4 minus 4AC, that is 12. Okay, and then divided by 2 times A. Okay, so negative 2 plus or minus, this is negative 8. So we have complex eigenvalues, and then S1 comma S2, we get, what's the square root of 8? That's it, 2 root 2I, isn't it? That's negative 8. So this is the I 2 root 2 divided by 2, and then this just becomes a negative 1 plus I root 2, and the negative 1 minus the I root 2. Those are the eigenvalues. Okay, all right. Now this most necessary though, yeah, but it's important to also know the eigenvalues. Okay, because maybe you're asked to find the stability of the system and all that. All right, so now let's find phi of t. So how do we find phi of t? Okay, so phi of t is equal to the Laplace inverse of Si minus A. Okay, inverse, right? So we know Si minus A already. We found Si minus A. Si minus A is equal to, okay, what was Si minus A? This matrix here, which is S minus 1, 3, S plus 2. Okay, minus 1, 3, S plus 2. Okay, now that is Si minus A. Now let us find the inverse of it. Okay, so what's the inverse of Si minus A? Inverse. The inverse of a 2 by 2 matrix simply what? The adjoint of the matrix divided by what? The determinant of the matrix. Okay, so the adjoint of the matrix is the matrix that you get when you swap the element in the major diagonal. Okay, and then multiply the elements in the minor diagonal by negative 1. Okay, so let's swap those guys. We have S plus 2 here, and then we have S here, and then if you multiply this in the minor diagonal by negative 1, this becomes negative 3. or the one becomes positive 1. Okay, and then divide by the determinant. The determinant is simply the characteristic equation that we just found here, isn't it? We found that determinant. Okay, so that's s squared, okay, plus c, s squared plus 2s plus 3. Okay, so this simplifies to s plus 2. Okay, so I'm dividing each element by this determinant here, s squared plus 2s plus 3, and then here we have 1 over s squared plus 2s plus 3, and then negative 3 over s squared plus 2s plus 3, and then finally I have s here over s squared plus 2s plus 3. So that's it, the phi of s. Okay, so this is this phi of s, isn't it? Okay, it's phi of s in s domain, right? When you take the Laplace inverse of this, phi of s will be able to convert to time domain. Okay, so I'm sure we're all fine up this far. All right, now let us find phi of t. Okay, remember that phi of t is simply the Laplace inverse of what? Phi of s, isn't it? So let us get the Laplace inverse of this. Okay, so for me to get the Laplace inverse of this, okay, so first time let me write phi of s. Okay, so how do we get the Laplace inverse of this? As you can see, the denominator here, okay, the denominator here is what? Okay, you can actually replace the eigenvalues here, but I'm going to show another way of doing it. Okay, so I'm going to complete the square. So at this point, you can replace the eigenvalues that you found. Okay, it's very much okay. So that's the reason you have to use those eigenvalues in factorized form, isn't it? Okay, so now what I'm going to do here, I'm going to complete the square. Okay, for each denominator. So it's just same denominator throughout. So I'll complete the square there. So this is s plus 2 divided by s squared plus 2s. Complete the square, I need to add half of 2, which is 1. I'll square it, subtract half of 2, square it, and then add 3, right? So I'll do the same thing throughout, okay? Because the same function. 2s plus 1 squared minus 1 squared plus 3. And then here also we have negative 3 over s squared plus 2s plus 1 squared minus 1 squared plus 3. Finally, here of s over s squared plus 2s plus 1 squared minus 1 squared plus 3. Okay, so now let us simplify this. So our phi of s will be equal to, this is s plus 2 divided by, so this is it. Remember, if you this part can be factorized, that's a perfect square, which is s plus 1 squared, right? If you factorize s squared plus 2s plus 1, that's s plus 1 squared. And then negative 1 plus 3, that is 2, okay? And then similarly here, 1 over s, s plus 1 squared, the same denominator, and then plus 2. Similarly here, you have negative 3, s plus 1 squared plus 2. And then here you have s plus 1 squared plus 2, okay? So this is our phi of s. Now we have to take the inverse of this, but before we take the inverse, you have to be very, very careful here, okay? So if you remember, here we have quadratic in the denominator, right? So it's like just remember this, right? Sine, the Laplace of sine a of t, right? The Laplace of this guy, okay, or a sine function. Remember that we have a on top divided by what? S squared plus s squared, isn't it? Similar, the Laplace of a cosine, okay, this is equal to s over s squared plus s squared, right? And then if you multiply by an exponential function, let's say for instance you have the Laplace of e to the power, let's say, negative a t, and then let's say cosine something, right? Cosine, let's say b. Okay, I'm just trying to use different values here so that they don't look the same. Okay, so this one here is for cosine function, this would be s plus a. Okay, the a, which is a power, the what, the coefficient of t, okay, in the exponential there, and then again s plus a, okay, squared, and then here plus b squared. Okay, b squared is the coefficient of t in the cosine there. Similarly, for a sine function, okay, the Laplace of e to the power negative at of sine, let's say bt, this is equal to what? B, okay, divided by s plus a squared plus b squared. Okay, so these are the Laplace, this is a Laplace relationship that we're going to use here. Okay, now if you notice here, it looks like this is what we have here, isn't it? On that, if you look at the power of exponential is 1. So this looks like a cosine function, isn't it? Somehow it looks like cosine, but the problem here, you have s plus 2. Remember, these have to be the same, isn't it? These have to be the same. So I have to do something there. So I'm going to separate this s plus 2. I'll write this as s plus 1 plus 1. Okay, and then divide by, so s plus 1 plus 1, I can just write them separately. So the first one, s plus 1, s plus 1 squared plus 2, and then another one, okay, the one that came from these two, I also write it separately using its own the same denominator, right? S plus 1 squared plus 2. Okay, now before we go any further, just see here. Okay, so this one looks like a sine now. Okay, this other part looks like a sine function, right? But remember that for a sine function, you need to have what? You need to have a b on top and b squared down, right? So b squared is what? B squared is 2. What is the b then? B is the square root of 2, isn't it? So b is the square root of 2. So it means that on top here, we need to have a square root of 2, right? Okay, for this to work, isn't it? The square root of 2. Now you can't just introduce number from nowhere. You just put a number there. What do? You divide again by square root of 2 here. Okay. Okay. You divide by square root of what? 2. So this is what we have now. Similarly here, it's the same thing, isn't it? Because we have the same thing even here, isn't it? For the other side, right? Okay. So what we're going to have here, we're going to have root 2, okay, over s plus 1 squared plus 2, and then don't forget divide by root 2. Okay, so that's the element that side, and then down there you see that we have negative 3. Okay, we have negative 3 there. So what do we do? Okay, so we can introduce root 2 again. This one looks also like a sine function, isn't it? Okay, it's a sine function because of a constant on top there. So again, we can write this as negative 3. Okay, divide by root 2. Remember, why am I dividing by root 2? Because I'm going to introduce root 2 on top. Okay, and then over s plus 1 squared plus 2, and then this other one of an s on top. Okay, so there's one problem here. You see you have s plus 1 here, right? You need to have the same thing here, because that one looks like a cosine function, isn't it? You need to have this relationship, right? So we need to introduce 1 to this s. So you're going to have s plus 1, but I can't just introduce number from nowhere. You have to subtract it, isn't it? Okay, so this s plus 1 over s plus 1 squared plus 2 minus, so since I introduced 1, I'm going to subtract 1. Now I'm just going to write this as two fractions, right? Minus 1 over s plus 1 squared plus 2. However, we have the same problem here. We have 1. Okay, this is a sine function, isn't it? So we need to introduce square root of 2 there. So we need to have a square root of 2 here. Okay, even here also divide by the square root of what? 2. Okay, so I don't change anything. So this is now our simplified matrix, right? Okay, let me just remove this guy here. Okay, so we have this matrix here. This is 5s, right? Now let's find the inverse of this. So 5t therefore will be the inverse of 5s, Laplace inverse of 5s. Okay, so this one here is a cosine, right? But there's an exponential, isn't it? Multiplied by exponential. This relationship here. Okay, what is our a, which is the coefficient of t, in the exponential there is negative 1, right? So this is e to the power negative t, right? And then it's cosine. Cosine what? Okay, what's cosine of bt? What is our b? Our b is the square root of what? That number there. This is the square root of 2, isn't it? Okay, and then plus, that is sine function. So amplitude there is 1 over square root of 2, right? This is a sine, isn't it? Again shifted. Okay, it's multiplied by an exponential. E to the power negative t. Again sine bt. What is b? The square root of 2 times t. Okay, and then here again we have the same sign. 1 over root 2 e to the power negative t sine of root 2t. Okay, and then finally we also have this here. It's a sine function again. We have negative 3 over root 2. Okay, and then that's sine root 2t, right? And then here we have cosine function, isn't it? That is it. E to the power negative t cosine root 2t, right? Okay, and then finally we have what? We have another sine function, minus 1 over root 2. Okay, e to the power negative t. Oh, sorry, here I forgot an exponential, right? Okay, e to the power negative t, and then we have what? Sine root 2t. Okay, so now this is our phi of t. Now to find the solution of this to this equation, remember we're finding x of t. X of t is simply equal to what? Phi of t multiplied by the initial conditions, right? Okay, so let us multiply that. Okay, so phi of t is that matrix there, e to the power negative t cosine root 2 t, and then plus 1 over root 2 e to the power negative t sine root 2 t, and then this side of minus 1 over root 2 e to the power negative t sine root 2t, and then down here we have negative 3 over root 2 e to the power negative t sine root 2t. Okay, and then you have e to the power negative t cosine root 2t minus 1 over root 2 e to the power negative t sine root 2t, and then multiply this guy by x of 0, right? So x of 0 is simply 1 negative 1 here, right? 1 negative 1. Okay, so you see this is a 2 by 2 matrix here, right? This is a 2 by 2 matrix, and this is a what? 2 by 1. So the order of the matrix will be what? 2 by 1 as well, isn't it? Okay, the first number here and the last number there. Okay, so we multiply those numbers. So row by column. So this is a row multiplied by the column, right? Isn't it? Okay, so we're going to have e to the power whatever multiplied by 1. So this is e to the power negative t cosine root 2t plus 1 root 2 e to the power negative t sine root 2t. And then this number multiplied by negative 1, that is plus, right? Okay. Okay, plus what? Let's see. There's something that I missed out here. What are the initial conditions, by the way? Okay, sorry. This is how did this negative 1 come about? Okay, this negative 1, I think I missed. I just introduced it. It's not here, right? Okay, yeah. This negative 1, yeah, it's on there. So this should be minus, isn't it? Minus, okay, 1 over root 2 e to the power negative t sine root 2t. Okay, so that's the first row. And then similarly here, the second row multiplied by the same numbers. So this guy multiplied by that, you have negative 3 over root 2 e to the power negative t sine root 2t. Okay, and then negative, this multiplied by negative 1, we have minus e to the power negative t cosine root 2t, and then plus, because this negative negative will be plus there, 1 over root 2 e to the power negative t sine root 2t. Okay, so this is it. Okay, x of t. Let's simplify this. So when you simplify this, what do you get? So this and that will cancel out, as you can see. So these two cancel out. So we have e to the power negative t cosine root 2t, and then here this and this will add up, right? So 1 over root 2 plus negative 3 over root 2, that is negative 2 over root 2, or same as what? Negative root 2, isn't it? This and that, try to add them, right? So that's negative root 2. Okay, and then e to the power negative t sine root 2t, and then minus e to the power negative t cosine root 2t. So this is our solution. Okay, so this is our x of t. So this means that our x1 of t is equal to what? So x1 of t is equal to e to the power negative t cosine of root 2t, and x2 of t is equal to negative root 2 e to the power negative t sine root 2t minus e to the power negative t cosine root 2t. Okay, so this is our solution. Thank you so much for your time and patience. Okay, see you in the next video.